B, right? Because it kind of helps them, it gives them practice to write down factors or to write down multiples, depending on if you're doing LCM or GCF, right? So you would do that method with somebody who needs practice with factoring numbers or writing multiples of numbers, because it quickly becomes just a silly, inefficient way to do it, right? So let's see. So GCF, you could do set intersection method, and what would that entail exactly? What would you have to do to figure out to use this method? Like if I wanted to figure out the GCF between what you got, Jeff? You got 40 and you got something else. There you go, buddy. Yeah, pick a number, 40. And then you can write down all of its factors. I love it, right? And we talked about some things I don't think most of you guys had heard about. For example, remember the turning point idea? Anytime you're trying to make a list of factors, how do I figure out, does someone remember what the turning point meant? Anybody?
It's like the other half.
Yes. When does that other half start? Because that's when things become easy. And one way we saw one of the little ones in one of our videos, she wasn't that little, but she sort of started with a number and then she put like 1, and so she would do 1 and 40. So she's making the pairs as she goes. Or you just want to know, when can I stop thinking and just start pairing? Does that make sense? So like here, I could do the square root of 40 to figure out that's roughly 6. So around 6, I should stop having to think and just start trying to pair numbers up. Is that cool? You never have to use that if you don't want to, but what the hell is out there? What's another way you can find a GCF? That's not set intersection method. Say again? Prime factorization, I love it. Sure. Prime factor method. So you would factor 40 and 25, and then you can sort of like piece together where they overlap. The biggest number that they overlap at. So this is where we saw one of the students make a mistake, right? You'll eventually get to 2 times 2 times 2 times 5. 25 would be, well, 25 is a silly number, Jeff, but that's okay. It's not a great number for this example. Let's do 28, sorry. Changing things in the middle, but too bad. 28. Okay. This would be 2 times 2 times 7. So if a student said 2 is the answer, because that's a number they see repeated, what would you say to them? I mean, 2 is a repeated number between the two of them, so why is that not right? Uh-oh.
Because there's 2 2s.
Yeah, so it's the greatest common factor, right? So whatever they both have completely in common, they both have 4 in common. They both do have 2, that is a common factor. That's not the greatest common factor. Okay. What's another method to find the GCF? You don't have to do it with these because they're relatively small, but remember subtracting. Right? Remember that? Subtracting, and that led to division and all that kind of stuff. But normally we use that if I need to cut the numbers down in size. Once you get to something like this, you should be able to kind of see it. But again, what would this be equivalent to? The GCF of what, for example? If I use the subtraction method. Yeah, 40 minus 28 is 12. So whatever the GCF of this is, must be the GCF of these. And then you can kind of keep going, but right. But normally you do that when you have these huge numbers and you want to cut them down so it's easier to look at. Is that right? So now, your actual question, you've been very patient. You're like, this is great, Jeff. This is so great. You gave yourself 2 numbers. Sounds like a teacher thing to do. What do I do when I have 3 freaking numbers? Well, how would this method change? Not that much. You just have one more tree, and then you have to compare amongst all 3. So let's say that the other number is, you can do it, Jeff. What is it? What's the other number? I don't know. 42. 2 times 3 times 7, is that cool? So now the answer can't be 4 because that dude does not have a 4 in it. So the biggest number that they all have in common can't be 14 because this dude's doesn't have a 7. So you could do prime factor method and just make one more tree. If you do it this way, all right, this gets a little weird. So for example, if I had to do GCF of, where do you go? 40, 28, and what did I just make up? 42. You can't really do the subtraction thing anymore, right? So basically, this is a really good way to do it. You could do, well, let's see. I don't think does the book actually give us like a specific, did I just skip that? I don't think they did like 3 factors too often. I think they only did it in one place. And that was when everything was factored, yeah. Are you looking at a specific problem, Bridget?
In set A, they have set A number 12 and C, or
Oh, okay.
like 12.
Oh, dude, yeah.
They have a bunch of those.
Use any method to find the following, okay.
So just prime factorization would be the.
Well, that's one method you could use, for sure. Now, the thing is, in this book, I wanted to double check I didn't miss something, because do you understand there could be an extension of a subtraction method for 3, but I don't want to go beyond, so there are possibly other things you could do. But yeah, prime factor tree is not a bad idea. Yeah, okay. And that sort of goes along with like number 12, part E and F, because they're already prime factored, right? Okay. All right. Yes?
What about number 13? Part C and D. Same section. Set A, 13.
So you use any method to find the LCM.
C and D.
C and D. Oh, okay. So let's do an example kind of like that. I looked at it really quickly, but it's got 3 of them, is that right?
Yeah.
Where's the commas? Don't get old, kids. Okay. So if I want to find the LCM of 2 to the 4th, 3 to the 3rd, 7 to the 5th, 2 cubed times 3 to the 5th times 7 squared, 2 times 3 to the 8th times 7. And I want to find the LCM. Who remembers how to kind of do that in this case? Let me say something. Like real quick, guys, real quick. What's the LCM of, what you got, Jeff? 5 and, that's silly. Let's do 10 and 25, sure. What's the LCM of 10 and 25? LCM, not GCF. LCM. What's the difference? So GCF is the biggest number that goes into each thing. LCM is the lowest number they both multiply up to be, right? Yeah, it'll be 50, right? So one way to realize what's going on here is, this one I can kind of do by making the set intersection method, because both numbers are relatively small. 10, 20, 30, 40, 50, 25, 50, bam, right? You guys with me? Okay. But if I want to kind of compare, so what did I just do? I just made a simpler problem. And let me make it look like that problem. 2 times 5, 5 times 5. Okay. One reason I want to put this up here, do you agree that the answer for an LCM problem has to have each number in it? That's the only way that can make sense. So 50 has 10 in it as a factor, and it's got 25 as a factor, correct? So the answer to this question, the answer to the LCM question has to have 10 in it, and it has to have 25 in it. Well, it almost has 25 in it. It's got 10 in it because I put 10 down. How do I make it also have 25? What else does it need? It's already got a 5, correct? So how do I make it have 25 in it? Give it one more freaking 5. Is that cool? And sure enough, what's that? That's freaking 50. Holy shit. So I can do the exact same thing here. Pick any of them. Write it down. Does this guy give any more information on top of that? Like, I already have 4 2s. He's only got 3. I got him covered. I put 3 3s down. Do I have this guy covered in terms of 3s? Shit, how many more 3s do I need? 2 more. What's the easiest way? Let me just do this. There we go. How about 7s? I had 5 7s. I totally got 2 7s. All right, let's look at the next guy. Does he add in? He's got 1 2. I got you covered. He's got freaking 8 3s. So I need 3 more of them. Is that cool? And he's got 1 7. And I've got that covered. Does that make sense? Okay, hopefully. Yes?
So your answer, like for the bottom one, would not be 50. It would be 2 times 5 times 5.
Which is 50.
But you don't like write.
Oh yeah, you totally do. If they want the LCM, this is the work, and then this is the answer. Yeah.
Oh, okay.
Is that cool? Yeah. Okay.
Because I think in the textbook it showed the answer.
Oh, for this one, totally. Yeah.
No, for the bottom one. I thought it showed some, like, I don't know, I could be wrong.
I think for these, they're like, don't worry about multiplying them out because it could get stupid big.
Yeah, that's what my problem was. That's why I was asking.
Oh, I
Like
see.
stupid big numbers.
Yeah, I think for these they'll accept it, and normally, very, very, very often in a math book or math class, the way that they give us the problem is the way we should answer the problem. So, like when I was teaching, and I won't go on a rant about I can't teach algebra, but when I taught Math 88 and we did mixed numbers and we did and I said if I give you improper fractions, I want the answer to be an improper fraction. If I give you mixed numbers, I want the answer to be mixed number. So here I would assume that they want me to answer this in prime factor form. If you're curious, you can multiply that stuff out and see what the hell it is. Real quick, does everybody see this? I really want this to make sense. Do you all see how now I can find each one of these numbers, I can find them independently in here. So that's at least a common multiple, and I put it together very carefully so it was the least common multiple. How would I find the GCF of those same numbers? Blah, 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 same numbers. I kind of do the opposite. I really, watch, here's a shortcut, you ready? I'm almost certain I told you this. Here's a shortcut for LCM of this kind of thing. What's the highest power in the 2? 4, right? What's the highest power in the 3? 8. What's the highest power in the 7? Done, right? You just put those together.
That's the GCF.
Say again? That would be the LCM, sorry.
Oh.
I'm just showing you a different way. So I did it very kind of lockstep. Write this guy down, add in any new information. But doesn't it make sense that if I just take the highest power of 2, it's automatically got all of them in it. It's got anything lower than that in it. Does that make sense? Okay. Yes?
If we were looking for the greatest common factor, that would it just be the smallest power? Like it would for 2, it would just be 2.
Yeah, so GCF will be exactly the opposite. It's got to be whatever the smallest power is. That kind of makes it nice and easy to remember. LCM, you're going to want the biggest thing that they all have. And I know, trust me, I understand. You're like, it says least common and you want me to take the biggest. It's because I'm multiplying it up, correct? GCF greatest, but I'm trying to divide it down. I'm trying to get the greatest common factor. So in this case, it would be the lowest power on 2 is first power. Lowest power on 3 is third power. And the lowest power on 7 is first power. So that would be the GCF. Okay, cool. Is that better? Okay. All right. Anything else from homework stuff? Okay. So there's one more thing I want to do from section 6.1. We'll watch the videos and then we'll do section 6.2. The one thing I haven't done yet from 6.1. Let me first kind of build off of where we got to. Does anyone remember if I give you 2 fractions, how to find a fraction that's directly in the middle of them? I want the fraction that is in the middle of those two. Well, what's one smart thing you could do immediately? So what would this be with the common denominator? Yeah, so 8/18 and 11/18. Now, if it was 8/18 and 10/18, Jeff, if you could have made that problem, the answer would have been 9/18, right? But no, I'm a teacher, so I didn't do that shit, right? Here's something I want you guys to understand. How do I find the number between any two numbers? I don't care if they're fractions or what they are. Do you guys know? Add them together, find the average. Add them together, divide by 2. That's a little gross here, correct? But now watch this. I want you to get, you ready? So add them together and divide by 2, correct? Okay, now watch why this is not that bad. What's 8/18 plus 11/18? 19/18. And I still got to divide by 2. What's happening to 19? Poor little dude's being divided by 18 and being divided by 2, right? So he's being divided by 36 total. No? Because another way you could have done this is you can actually make them both, keep building on them until you get a nice whole number between these two. So this would be 1636, this would be 2236, and right between there is 1936. I don't know if you guys see that, but this method is really freaking cool. How do you find the fraction that's between any two given fractions? How do I find the fraction between them? I add the top, well, assuming they're already the same denominator, right? So the first step is make them have the same denominator. You can say the word, Jeff. It's okay. And then you just do this. You just add them, but then you double the bottom. I really want you guys to see. I do A plus C divided by 2. I got to divide, add them up, divide by 2. But there's also already a B down there, so it just becomes twice as big. Yes, it's a little shortcut. You don't have to do the shortcut if you don't like. You can do like we did here.
So in like that situation, that would be an okay answer to put, like, just because that is. If you
That
do
is
something-
the fraction that is between, that is
Yeah.
exactly in the middle of those two, yes. Yes. Now, so that's a little shortcut. Or you add them and divide by 2. And real quick, what's division by 2 mean? Multiplication by a half. We'll see. I love talking about that. Have I shown you why that's true? I haven't shown you why that's true yet. Do you guys remember? Does anyone know when you divide fractions why you multiply by the reciprocal of the second dude? Does anyone know why you do that? I don't think I've talked about that yet. Yeah, we're not quite there yet. Okay, I'm going to show you why. And some of you guys are like, it's okay, Jeff. I don't need to know. I want you to know, so I'm going to show you. Okay. So, what if I didn't need the fraction that was right in the middle? What if I just wanted any fraction between the two of them? Can somebody tell me, if you give me any two fractions that aren't equal to each other, how many fractions do you think exist between them? Somebody give me a fraction. Somebody else give me another fraction.
7/8.
Say again?
7/8.
7/8. I love it. How many fractions do you think exist between those two? Infinite number. I love it. Is everybody okay with that? Because again, I can make this become 8 and I can find a number in the middle, but again, so this would be 4/8 and 7/8. So isn't there 5/8, 6/8? And between 5/8 and 6/8, isn't there some 16ths? Right? In between the 8, so there's another, you just keep going down. Now you can just keep making it on there bigger and bigger and bigger. What's the limit on how big you can make a number? There isn't one. So that there's an infinite number of fractions in the middle. Crazy. Okay. Now, what if I just wanted any fraction between those two? Here's a claim I'm going to make, and then I will prove it. If I just wanted any fraction between those two, I could just do this. that should, now it doesn't hurt me. If I saw a student do that when I asked them to add them, that would kind of hurt me. I would physically feel some pain. That does not hurt me at all. It should hurt you a little bit. That should, because you don't know why the shit that's true. When am I ever able to just add the tops and the bottoms? Are you with me? That is one reason why I'll be very careful with who I show this to. Because this might reinforce incorrect thoughts. Real quick, can you guys, let me see, can you show me that 4/5 is between 1/2 and 7/8? Can you guys come up with a way to show that? What does it mean if it's between? That means that 1/2 is how related to 4/5, is how related to 7/8. If a number is between two, it's got to be bigger than the smaller dude and smaller than the bigger dude, right? How do you verify that? We talked about that last time, and you're all like, dude, last time, there's a week in between. I know. Does anyone remember there's something about cross multiplication in a weird place you wouldn't expect it to show up? So if I do, okay, I like some of you guys' expressions are like, what's going on? If I just look at this guy by itself, does anyone remember how to show the inequality here is true? Don't you do 5 and 8? Which one's bigger? So that verifies that's the right direction. We talked about that last time. Here, I don't have to write it in. Look, 32 and 35, which one's bigger? 35, so that's pointing the right direction. So 4/5 is between those two. So let me show you the proof. Right? And you're all like, oh, I love it when he does proofs. It's fantastic. All right, sorry. So proofs are always exciting because I've got to start with just letters. If somebody gives me two fractions, the only time, when would it not make sense for somebody to ask me to find the fraction in between if the two fractions are actually already equal? Then there's no fraction between, they're the same superfraction. So if somebody gives me two fractions and the question makes sense, one of them has to be smaller than the other one. You guys agree? You're like, sure. Right, so I'm just going to say that one's smaller than the other one. One of them has to be. What this means is, basically using what we just did there, AD must be less than BC. Is that cool so far? Okay, I like it. Now let's see if I can remember. Let's see. You could do it, Jeff. You could do it, buddy. Oh yeah, okay. So AD plus AC would be less than BC plus AC. That's an old thing we learned before. If I add the same thing to both sides of an inequality, it stays the same. Is that cool? Stay with me now. You're never going to have to do this yourself, okay? Unless it's a bonus question or something, right? But follow me. I want this to make sense. So right now it's kind of like, why the shit did you add that, Jeff? All right, well, let's see. Can't I take an A out here? Did I do this the right way? I loved it, Jeff. All right. Why did I add AC? Let me see. What did I actually want to add? I actually want to add AB. Okay, you'll see why. I can add whatever the hell I want to, but there's a reason why I want to add AB. Yes, there you go, buddy. I could just think ahead. It doesn't matter if what I add. I can add whatever I want to. AB specifically will help me. So watch this. I can take a B out of here and A out of there. Stop for a minute. I know. I don't know on one level if you guys just look at this like some weird math guy just playing around with letters. Does each step make sense? We're getting there. We're getting there. I can divide by B, yes. And I can divide by D plus B. Let me write this in alphabetical order. Okay. So look what, I love some of your expressions. My claim that I made earlier was if I'm given two fractions, I should be able to just add them together to get something between them. What have I shown so far? If I do just add the tops and bottoms together, it is bigger than A over B, right? All right, let's see. I'm going to lose a few more of you now. So I've got to keep going. I got to prove the other way. So what if I start over again here? And I do this instead. What do you want this time, Jeff? I want this, yes. And by the way, I really kind of want you, do you see how no matter what, I want to be able to get this, right? I have to be able to get this, correct? So do you see how now if I take a D out, I'm going to get A plus C, and if I take a C out, I'm going to get B plus D, which is exactly the two things I kind of need. So this will be D, A plus C. This will be C, B plus D. If I divide by B plus D, and I divide by D, I get A over B is less than this, which is less than this. Therefore, this is between those two. I like it. All right, so what does that mean? If I give you two fractions and I just say, find a fraction between these two, you just add the tops, add the bottoms, you're done. Right? If I specifically say, I want the fraction that's exactly between these two, you gotta average them. This way just finds some fraction. Are you with me? So what would be some fraction that's between 2/9 and 11/15? 13/24, right? Kick ass. Okay, so that's just a known fact for you now. You just know it. I like it. Okay, so let's do this. Let's watch. Let me think. Okay. So we got what they want from this? More than you ever wanted? Okay.
So is all that just proving it further?
No, it's
Or is that
proving it
like-
in the first place.
Oh, okay.
Yeah. I hadn't proven it until I did this. Hello. Okay.
So in order to add fractions together, we have to have the same denominator. So when we cross multiply, we have to put both of these under.
All right, guys. So I am in the candy corn group. It's just me by myself. Oh well. I love candy corn, so it works out for me. All right. So I just helped one group with this first one. What I really want here is not a few examples. A few examples is not a bad idea. Give yourself a few examples. What's got to be true about a fraction so that it is also a whole number?
The numerator and denominator are the same number.
That's one possibility, but that's too specific. So if the numerator and the denominator are the same number, the whole number it will always be as 1, right? Can you not come up with a fraction that also represents 2? 2 over 1, 4 over 2, 16 over 8, right? So there's a few different ways to answer this. One way I helped one group figure it out. Can you guys tell me what the hell we came up with?
I forgot. What's something that would
Jeff, everything you say is so important that I, go ahead.
something that reduces to
Something over 1. I love it. So if it reduces to something over 1, right? Then that's a fraction. That's a whole number. That's also a fraction. So 8 over 4. Can't you reduce that to 2 over 1? Which is 2. Another way to look at it is if the top is a multiple of the bottom. Right? So if I put 11 on the bottom and I put a multiple of it on the top, won't that become a whole number? So the purpose of that first question was, give me a description of what a fraction would look like that is also a whole number. So a few examples, beautiful way to go. Just to feel out what the hell this problem is trying to say to me. right? And eventually you're gonna get to something like it's gotta reduce to something over 1, or I like this even a little better, the top's gotta be a multiple of the bottom, right? There's no other way that a fraction could be a whole number. You guys agree with me? Most of you guys are like, go to number 2, okay. This one, I didn't really 100% know how to say this. This first one you could do very easily by making the denominators the same. But what is the kind of like method we were using? This is one place you cross multiply. That seems a little out of place. And then you just say, what would go here? Greater. So then what goes between these two? Greater. So as long as you pull that dude up here and this dude up there, their relationship is exactly the same as the fractional relationship. And we actually proved that last Thursday. Okay. So here, same thing, just, much bigger numbers. So yeah, so you can use your old calculator, and you should get, I can't remember, what is it now? Sorry. And you get that both ways, right? So this one obviously is equals 11. Kick ass. Okay, we're almost to the part that's really nifty. That sounded terrible. Only one part of this is really nifty. Number 3, what's the shortcut to find any fraction between those two? Add straight across. And again, somebody was a little troubled. I understand the messaging that I gave wasn't the clearest. You guys can do this all day. What I said was be careful who you show it to. Because there are people in the world, and sometimes they take my calculus course, for example, and they think that 1/4 plus 2/5 is 3/9, and I have tears coming out. I'm like, well, how did you get here? Okay. Do y'all understand? So you have to be really careful who you show this to, because it will reinforce the wrong thing. They'll say, oh, look, you just added them, I must be able to do that. But this is a very specific application. I'm not adding these fractions. I'm trying to find something between. It just so happens that adding these together accomplishes that. I like it. Okay. If I ask you to prove, to show me this is between those two, what would you do? Well, if I were you, I would write this, right? And then you can do this, verify that, you can cross multiply here and verify that. Is that cool? We did that earlier on the board. Yes? 27, yeah, thank you. I'm too close to it. It's all right, you guys, trust me. I am not the kind of teacher. Have you ever had a math teacher who's like, I never make mistakes? I make some mistakes, so yeah, thank you. So if I cross multiply, just like we did up here, I can verify that the inequality is the right way. This one's the nifty one. Okay, this one I felt a little silly because I knew this and I totally forgot about it. Let's do this the straight up way. I think most of you guys did this. How do I find the fraction exactly halfway? What do I do with these? Add them together and divide by 2. So eventually you get 17 over 30, right? Let's see if Jeff can add correctly this time. Okay. What I really want you to understand, the other method, real quick. So if I have 2 fractions and I want to find any fraction between, it would be a plus c, not equals to, but a plus c over b plus d, correct? With me? What if the denominators are already the same? Get out of there, plus. What if the denominators are already the same? This would be a plus c over b plus b, yes? But if I add these and then divide by 2, do you see how these are the same? So if the denominators are the same, if you add straight across 8 plus 9, 17, 15 plus 15, 30, you do get a fraction that is directly in the middle. Do you guys see that? Okay, so in general, adding straight across just gives you a fraction somewhere in the middle. If the bottoms are not the same, it's not going to be right in the middle. If the bottoms are the same, this process gives you right in the middle. Okay, I like it. So what about number 5? I just kinda threw this in there to see how much you guys remembered about working with fractions. What do I, of course, do first here? Yeah. What do I do in the parentheses to do this? Common denominator, so I gotta multiply by 2. So I get 10/4 minus 1/4. So I get 7/6 plus 9/4. And how do I do this? Again, I need common denominator. So remember this real quick. I need an LCD. Does anyone remember the shortcut to do it? 6 times 4 is 24. That's not the LCD because these two share a factor, correct? So if I multiply and divide by the factor they share, that is the LCD. It's not always easy to tell when the numbers get big what number they share. So it's not the greatest way to do it. But for small numbers, 24 divided by 2, 12. 12 is the LCD. I love it. So I get 14/12 plus 8, yeah, they're 18, plus 27/12. It's just your job, Jeff. 41/12. And then, I don't think did I say? Oh, I did. Mixed number format, right? So how do I do this into mixed numbers?
3 and 5.
Yeah, 12 goes to the 41 3 times with 5 left over. Is that cool? All right. By the way, short little side note, 36, 12 would go into 36 evenly and there would be 5 to make it 41. So it's just another way to see 3 and 5/12. Okay, I like it, yes?
Can you give them a common denominator from the beginning? Or do you have to?
Well,
No.
oh, you mean all 3, sure, yeah.
Okay.
From the very beginning, you can make all 3 common.
Yeah.
Yeah. The reason I wouldn't do that is the inside, once you put them together, it might reduce.
Okay.
And then the common denominator is smaller. Does that make sense?
Yeah.
But yeah, you could have. All right, so this is the part that, as an elementary teacher, you are gonna have to represent this for parents that aren't gonna understand. This is the whole big battle I sometimes see on, I don't know if all you young kids know about it, there's this thing called Facebook that a lot of old people are on. And normally they use it to rant and rave about stuff or to put these silly PEMDAS problems that nobody can do correctly. So Jeff is crying again. But they'll also talk about, oh, my son or daughter came home and this teacher said that 5 times 3 is not the same as 3 times 5, and oh my God, so we have to understand that when you are first showing a student what multiplication is, they have no idea about commutativity, they have nothing, they just know about counting things. So if I have 5 groups of 3 things, that is very different from 3 groups of 5 things. Those are different physically, right? 5 people, they each get 3 things, 3 people, they each get 5 things. That's a completely different day, right? From a student perspective, like, yeah, I'm gonna have 5 versus 3. So, for example, 3 times 5 meant 3 groups of 5. 5 times 3 meant 5 groups of 3. So that's why this one is physically easier to think about. Because what do I have? How many groups of what do I have for this first guy? Say again? I have how many groups of what?
8 groups.
8 groups of a half, right? And by the way that I say that, you can see this another reinforcement that of means multiply, right? 8 groups of a half, so I got a half plus a half, 8 times. So eventually you get 1/2 plus 1/2 is 1, you get 4, 1, so you get 4. Okay. So a parent would say, what the shit is your problem? That's just the same thing, but again, physically, what would this represent? So I saw a lot of different ideas. One idea was, let me think. Ryan, I'm thinking about what you had down there. Describe what you had down there.
You mean like what I wrote?
What you drew.
I put like,
Not the circle one.
I put
Yeah.
a box.
Yeah.
With 8 squares, and then I shaded it.
And you had like, oh, you broke it up into
Right.
just 1, 2, 3 like that?
Yep, and then,
Then you cut it. Oh, so now you got 8, okay.
Yep.
And then what'd you do?
and then shaded it before.
And then you shaded in half of those.
Right.
So that's 4, okay, I like it. That's a visual representation of half of 8. I like it. Now, and of course, if you try to describe this the same way we describe this, we would say we need half a group of 8. And you're like, what the hell is half a group? Right? Well, it's exactly this. If a full group is 8, half a group would be 4. Right? Okay, yes?
Wouldn't students see that as 4 eighths?
Oh, sure. Yeah. That's where you gotta be. It's not a bad idea. And again, if I relate it back to when we did this, that would be 3 times 5, yes? And this is before we talked about fractions, right? So there would be 15 total squares, right? So as long as you put it in that context, that would be okay. But you're right, it's, you gotta consider what frame is your student's brain in. So if you're doing a lot of region models for fractions, they're not gonna look at this, like Brooke said, they're gonna see eighths, right, not halves. So you could put like 8 distinct things down, and then chop it in half, and there would be 4. Yeah. Okay. So I like that. Okay. Anything else from this sheet here? Obviously, this is a little bit of a precursor because this is section 6.3. And I put a little bit of section 6.2 up here. All right. So if you guys want to wander back to your locations. Oh, let me go back to you. So, let me see if you guys, can you take a minute, figure out how to represent this problem visually. Yeah, doesn't matter. So how could you set this up, or how could you walk a student through how to do this visually? Yes.
For me, the pi method worked really well when I was younger, like just cutting it, like
Yeah,
every
cool.
time I had a fraction, I would always do the pi method.
So let's see. So for 5, I think it's going to be. Did I do this right? Let me see. For 5, it's a little freaky. So I have 1. I could draw this, couldn't I? Yes. You could do it, Jeff. There we go. Okay, it's not too bad. I like it. What would you do with this pie? You could do this whole problem in one pie, or you could do it with a couple pies. It's up to you. I don't know. So what'd you do?
I like colors, so I would
Good.
do
Yeah, I'm ready.
like the 1/5 in one color and then the 3/5 in another color.
So I got the 1/5 in purple, and then the 3/5 in blue. I like it. And then you would say to the student,
How many slices of pie are shaded?
exactly, right? So at this point, the student, if you gave them just one fraction, they would be able to draw some region model, some shape, and shade in like 1 out of the 5 shapes. So they know how to do that. So, and also you would do several problems in reverse, right? So if you gave them and you said, okay, what fraction is this? you know, 1/5. Okay, so they is that right? I'm not trusting my math anymore. So they know a finished pie, they know how to kind of write this as a fraction. So they drew this themselves, and then they can immediately see this is 4/5, and then you can kind of start to make the point about how to add fractions that have the same denominator. So if they have the same denominator, it kicks ass, right? What's easier for me when I used to teach Math 88, I used to be able to do this. You're not going to be able to do that with certain grades. You're not going to, unfortunately, have talked about algebra. Although I know there's a few places that are trying to infuse algebra a little bit earlier, which to me only makes sense, just so they're more comfortable with it. It's the difference between learning French in 11th grade versus learning French in kindergarten, right? That's what it is. It is crazy hard to learn French, whereas in 11th grade versus kindergarten. But I like to show this to students who know a little algebra because they know about like terms. So I like to try to explain fractions in terms of like terms. I have one of these plus 3 of the same thing, so of course I got 4 of those, right? Okay. So what about, is there another way to represent it visually? Anybody else do it a different way? And not just a different shape, because I could use rectangle, whatever. Is there another way to represent it visually? Is there another way we've represented fractions visually?
Do separate charts.
Oh, like separate, okay, so that'd be sort of like,
Same thing.
you'd have, so this would be 1/5 of all the items,
Yeah.
and then 3/5 of all the items, yeah, okay. How about number line? So if I go 1/5, and then from there I go 1, 2, 3 more fifths, that gets me to 4/5. So what is really kind of funny to me is, it's not arbitrary, obviously, but let me see if this makes sense to you. I'm kind of working on this. We build everything off of ones, kind of naturally, and which makes sense, because when we were cavemen or whatever, cave people, we would collect rocks, and we'd use rocks to hunt or whatever, or to decorate our caves or whatever, and we want to know how many rocks do I have, right? Even if we broke it in half, now I've got 2 rocks, 2 smaller rocks, look at me go. So I don't have to have fractions and all that kind of shit, you with me? So it made sense naturally to start to base everything off of a whole 1. So 3 whole 1s, we call that 3, right? And then 2 groups of 3, we call that 6. But couldn't I base everything off of fifths? Couldn't I have looked at my finger and said, okay, that's 1 out of 5 fingers. So to make a full hand, I would need 5 fingers. That'd be 5 fists. That makes a hand. Are you guys with me? Okay, I like it. I don't know if that makes any sense. But part of the misunderstanding about fractions is we base everything off of 1 so deeply that when fractions come to play, they are completely like out of nowhere, right? There's some applications students totally understand. If my mom said, I'm gonna throw out half your toys if you don't pick them up, okay, I understand that. I'm gonna use that. Okay, let's get this stuff off the floor. You with me? Okay, I like it. So that's another way to show it visually. So yeah, so unfortunately, with certain ages, you're not going to be able to talk about 1x plus 3x necessarily, right? But you could talk about, 1 chair plus 3 chairs. Well, that's 4 chairs, right? But what's 1 chair, Cherry, Jeff, good job, plus 3 dogs? That's not 4 dog chairs. That's weird. I don't want to go to your house. Are you guys semi with me? So again, you can sort of talk about the idea of like terms without bringing algebra into it, which is all fractions are all about. If they're describing the same number of parts, then combining them is easy as hell, right? Okay. So, just to kind of like formalize something that we all already know, if I have A over B plus C over B, That will equal A plus C over B. That is crazy sauce. That's amazing. What about A over B plus C over D? Let me see. Could you guys just add those? Could you just add those? Does anyone feel comfortable actually not giving it numbers, just adding A over B to C over D? Could you do it? I think you could, right? Because you know how to do. You totally do. What is this first dude missing that he's got? Let me make this bigger. Yeah. So this first dude is missing a D. So you have to do it to the top and bottom, right? And then what about this guy? What's he missing? D. So then you would get AD plus BC over BD. Now what's one little thing about this that we need to then improve on? This is kind of assuming that B and D are how related to each other. What is the one time that the correct thing is just to multiply the two denominators together? Like if I do 1/4 plus 1/20, do I have to make them 80ths? They have a common factor, right? So this is the correct way to kind of do it if B and D are relatively prime, right? So if I do 1/7 plus 1/8, it will be over 56 because they both need each other. If they share something already, they don't both need the other fully. They just need part of the other one, right? Okay, maybe. So this is a correct answer. It could just sort of make all the numbers get way bigger than they have to be, right? Okay. Tell me in the background of all of this. I haven't written this down in a while because I think at one point I just said a blanket statement. What is true about A and C? When I write stuff like that, what is true about them? Do you guys remember? What kind of numbers are they? There's a certain kind of number we haven't really officially brought into play yet. But what kind of numbers, A and C? Does anyone remember? Somebody create a fraction for me. Just create a fraction, tell me. 3/4. Why did you pick 3? Why didn't you pick square root of 3? Why didn't you pick 3.9? All right, so what's true about A and C? Whole numbers, kick ass. You with me? And what's true about B and D? Well, here, B and D. What's true about B and D? They are also, except they can't be 0. I love it. You guys all with me? Okay, so two fractions, when I add them together, I get basically the addition of two whole numbers, correct? So every property that whole numbers have, commutativity, associativity, identity, right? Distributivity. Every property that whole numbers have, fractions inherit. Does that make sense? Because they are composed of whole numbers. In fact, when I add these together, the bottoms don't really matter. They sort of like come for the ride, right? It's the tops that I add together. So does that make, I really want that to make sense. You inherit all of the properties of whole numbers because fractions are composed of whole numbers. Okay, maybe. So what does that mean? That means if I add two fractions together, what kind of answer can I get? What kind of answer do I have to get? This is the idea of, I don't know if this is good enough. You know, like, your charades game is off, Jeff, but they have to be closed, right? So if I add two fractions together, the answer must be a fraction, right? Closed meant if I add two whole numbers together, the answer must be a whole number, correct? I like it. So some of you guys might say, well, what about 1/2 plus 1/2, Jeff? I'm like, it's 2/2. It's 1/1. That's still a fraction, right? A fraction is a whole number over a whole number where the bottom's not 0. Also, what about this? Yeah, let me jump ahead a little bit. Yeah. how would you do this? All my markers are dying, it's sad. Does anything jump out at you about that we've talked about relatively recently? There's a certain series of things, a couple of them started with something. No. Well, how would you do 4 plus 8 plus 6? You would first do 4 plus, compatible numbers. So what are my compatible numbers up here? Shit, not just because they have the same denominator, but because together they make a whole 1, right? The equivalent of like a 10, yeah. Okay. So now what properties do I have to use just to get really pedantic, right? What properties must I use? What properties must exist for fractions to be able to put those together? There's at least 2. Am I currently allowed, the way it's written, am I supposed to add this to this? Nope. So what 2 properties could I use? Don't I want to move the 5 7s to be with the 2 7s? So I at least want to use commutativity. But there's parentheses around there, so I also need to use associativity. I like it. So, did all of you guys, does anyone live in this room? If you do, I'm sorry. You got to let me know. Nobody lives, okay, Jeff, whatever. All of us commuted to get here, correct? So I try to tell students, individuals commute, parentheses associate. So when parentheses move, that's associativity. When individual things move, that's commutativity. So if I first do this, which is ground shaking, I know, and then I just shift the parentheses over. So that's what property? Commutativity. And then I just use, I don't know why I'm making it brackets, but you know, these things happen. What property is that? Associativity. And then, you know, but I understand. This is where you have to live. Because your students don't look at that and say to themselves, oh, of course 2 7s and 5 7s can go together. You guys have internalized commutativity and associativity. You don't have to stop and think about it. You just sort of like, put it over there. There we go. They're not going to know that yet. They're not there yet. So you have to put yourself at the level of, okay, I can't assume they know what's going on. And of course here I'm going to get what? 7 7s. I like it. So I get 1 1/4. And then you can make them change it into an improper if you want to, right? Is that cool? All right. Did we talk about, real quick, did we talk about why the process of changing from mixed number to improper fraction works? Do you guys know what the process is? How do I change that to an improper fraction?
Multiply 4 by 1 and then add
4 times 1 plus 1, right? So why does that work? You're like, dude, I told you how to do it. Go back to this. Remember what I said? This is one of the most unfortunate choices in history of notation. Because normally, what does it mean when 2 things are sitting next to each other? What operation does that mean? Multiplication. This does not mean multiplication, correct? Otherwise, 1 1/4 would equal 1/4. That would suck, right? So what's the understood operation between? Addition. Mixed number, why is it called a mixed number? Because it's got a whole part and it's got a fractional part, correct? So there will always be a whole part, and what's underneath that always? What's always underneath the whole number? 1. Do you see whatever the shit number that is what this needs to become, and since it's always got a 1 on the bottom, you're going to multiply that by these to see that. No matter what that number is, I'm going to multiply those by it. So see the first step, 4 times 1, that's where the 4 times 1 is coming in, yes? And of course, then what do? I'm going to write that very pedantically. Today's just a pedantic day. It's just weird. And then I do what? Add these, yes? 4 times 1 plus 1. 4 times 1 plus 1. That's why the shortcut works, right? Okay. You really need for yourself, as you prepare to teach elementary students, you've got to identify the shortcuts you have been taught and you have developed. And you've got to really say, why does it work, right? I think one of the worst things a math teacher can do, besides being inflexible with their students, is to teach a shortcut and never explain why it works. So many students are just like, I don't know why, this guy just told me. And that kind of reinforces the idea of, yeah, whatever you tell me to do, I'm just gonna do it. And then that develops zero understanding. And if you have no understanding, you have nothing to build on, okay? All right. So I could do mixed number, I could do improper fraction, whichever way you want. Oh, blah, 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 blah. Oh, okay. Couple more things, then I'll let you out of here. If I wanted to do, oh, that's right, I forgot about that. One thing here. What if I want to do 1/4 plus 1/2, but I want to do it visually? Bless you. This is where I would say you should do two things, right? Here's 1/4. How would I represent 1/2? Chop. Right? You guys with me? Now, do you see how they go into each other nicely? I don't know if you guys. So you could either see that these are the same size, right? So going along with you, I should have made this in a different color, but it's too bad. So if I add these two together, it ends up being green. You let me down, buddy. Yeah. And then these are actually this. That whole block goes there. But what's a better way to look at this? So you could look at it that way. What goes along with what we actually have to do mathematically?
Just find the, like, figure out why they go into each other. So I would have cut like that half. into
Good,
four.
but I want to make a point. Visually, you totally can see that that block just fits right there. So the answer is 3/4. So the student can still see visual. Okay, it's 3/4. And then they say, does this change anything really? Did I actually change how much is shaded? No. But now this is not 1/2 anymore. This is now 2/4. But if I put that with this, it's still 3/4. So that's reinforcing a couple things. 1/2 does equal 2/4. If I make the denominators the same, if I make the number of little parts the same, it's easier visually to put them together, all that kind of stuff. Okay, I like it, I like it. Yeah, so if I want to do this, okay, something nice. If I want to do that visually, what would you do? This one's kind of nice. Like denominators makes everything beautiful. So this is basically exactly the same idea as like Pedro has $3, Ella Steele's $1, right? Yes.
You do like number line.
Okay, you could do number line, sure, I like it. 1/4, 2/4, 3/4, 4/4, 1. So yeah, so you start at 3/4, and then you go back 1/4. I mean, that's the way I was thinking about it, right? Does that make sense? Okay. If you want to do it with the blocks, you got 3/4. There you go, Jeff. Good job. And then you actually just, not physically, but you go, all right, remove that one. Are you going to erase it or whatever? So then, of course, you're going to have 2/4 left. Okay. I like it. All right. Nothing amazing here at the moment. Oh, that's the last thing I want to do. I think, yeah, well, okay, that works out good. Yeah, okay. I was one thing I wanted to do that I don't think I necessarily want to get into right now is I want to do a few things with the fraction manipulatives. You guys barely got to use them so far. I want to do a few things that leads into, for example, how to do this problem here. Right? A few different ways to do that problem. Do you guys see the inherent issue with that problem? It's sort of like I have to do something related to borrowing because the things in my ones place, not really my sixths place, the top is smaller than the bottom. I can't subtract, right? So what would it look like with manipulatives to do this? You can start to imagine what that would look like, right? So I think we'll do that next time. I think we'll end today now. You guys can go have a little extra time to get ready for whatever's happening. And I hope you have a good time, and I'll see you Thursday.